Okay, so now that we have an idea of all the different physical states, solids, liquids, gases, as well as the transitions between them, we're going to put all of these together now in what are known as heating curves, or sometimes they're referred to as cooling curves, which is just the opposite way of looking at this. And what these are going to do is that they are going to chart the change in temperature as a function of the amount of heat added. Okay, so this is going to be analogous to a graph that we're going to be taking a look at, where we see how the temperature changes as we add more and more heat to a system. So let's take a look at a very simple example. Imagine that we had on the y-axis, and then we had on the x-axis the following. So on the y-axis, we have temperature, and we'll say this is degrees Celsius. And on the x-axis, we're going to have heat added. And this is going to be in joules, which is a unit of heat that we talked about, which is abbreviated J. So we're going to start off with, let's say we have a sample of water, specifically now ice. So that's solid water at -20 degrees Celsius. Okay, so we're going to start with this. So on our temperature scale, let's say this over here is -20, and then we go up -10. This is 0 degrees Celsius. And we have 10, 20, 30, 40, 50, 60, 70, 80, 90, and then there's 100 degrees Celsius and 110, 20, 30, 40, etc. Okay, so I'm just going to put some more numbers in here. So 10, 20, 30, 40, 50. So we're starting right about down here in the lower left portion. We'll do this in orange. That's where we're starting off. Okay, so we have a sample of ice. It's super cold, -20 degrees Celsius, and we're going to start adding heat to it. And as we start adding heat to the sample of ice at -20, the temperature of the ice starts to increase. So as we add heat, the temperature of the ice increases. It goes up, goes up, goes up, goes up. We keep adding more heat until we get to a particular temperature, specifically now at 0 degrees Celsius. And at 0 degrees Celsius, this, as you probably know, is the melting point of ice, or the freezing point of water if you're going in the opposite direction. And at this temperature, once we reach that temperature, if we keep adding more heat, what we notice is something very unusual, is that even if we add more heat, the temperature actually stays constant. So we add more heat, add more heat, add more heat. The temperature stays constant. And why does it actually stay constant? Well, at this point, or during this region here, okay, what's actually happening is the ice is melting. So we're going from solid ice to liquid water during this phase. So all the energy that is going into, all the heat that is going into this is going into converting the solid ice into the liquid water. Right? So remember, in the solid, the particles are really, really close together. They can't move around. And when it turns into a liquid, those particles can move a little bit more freely now. So the energy that goes into this goes into converting the solid to the liquid. In this first initial portion here, right, the slanted region, what we have is the temperature of just the ice is increasing until we get to the melting point. So we keep adding more heat, we add more heat, add more heat, until eventually we get to the point where all of the solid has turned into liquid. So at this point here, all of the solid has turned into liquid. So we only have the liquid phase now. And if we keep adding more heat, we see that the temperature of the liquid now starts to increase. So we add more heat, keep adding more heat. The temperature of the liquid water is increasing, keeps going up, keep going up. We add more heat, temperature goes up until eventually we get to 100 degrees Celsius. So in this other slanted region here, So in this region, we have now just liquid water. So liquid water only in this region. And here the temperature of the liquid water increases. Until we get to another important temperature point, that's at 100 degrees Celsius. This is the boiling point of water. Under normal conditions, it boils at 100 degrees Celsius. And if we keep adding more heat, well, that heat goes into converting the liquid phase to the gas phase. So at this point here, this flat region, this plateau, we have the liquid turning into the gas phase until eventually we added so much heat that all of the liquid has turned into gas. So that'll be right about here. So now all we have is just gas. If we keep increasing the amount of heat, well, then the temperature of the gas, the water vapor, increases, right? So we'll change that to vapor so we're consistent with the terminology. But remember, gas and vapor are the same thing. So here we have liquid turning into the vapor, right? And that's happens at the boiling point. And after that, this slanted region where the graph slope upwards, that represents where we just have vapor only. And yeah, the temperature of the vapor increases, right? Steam, in other words, is what we're looking at. So what you'll see in a typical heating curve, and this represents the heating curve for water starting off at negative 20 degrees Celsius, is that you will see plateaus, flat regions on the graph. And these flat regions represent phase changes or changes in state. Okay, so going from the solid to the liquid, right? That represents fusion or melting, which we talked about before. And then going from the liquid to the vapor, well, that's vaporization. Okay, and at those temperatures, at those regions, the temperature stays constant, and that's how you can recognize a phase change on a heating curve. Is that the curve actually, or the graph actually is flat. It's horizontal. There's a plateau that represents one phase changing into another. So this is a heating curve for water. If you were to go in the opposite direction, so if you start off up here, let's say, up at this point, if you were to start here with steam, and then you take heat away, and you go in the opposite direction, going in this general direction, well, then that would be a cooling curve. So now we're cooling the sample down, temperature goes down, and we'll see the reverse of these processes happening as well. Okay, so both of those are used, and this is a much more efficient way to represent all of those changes that are occurring. In chapter 3 of the Gann textbook, it does talk about these different, it kind of summarizes everything, but it doesn't give you sort of a graphical representation. But this, I think, is a quicker and a more efficient way to look at it.